The first question asks us to construct Lewis diagrams for carbon dioxide and carbon tetrachloride. So, starting with carbon dioxide, first we want to take count of how many valence electrons are present in this molecule. So, carbon is going to have 4 valence electrons, and oxygen has 6 valence electrons. Now, since we have 2 oxygens present in this molecule, we're going to double that, and that's going to give us 12 valence electrons. So that means total, I'm going to have 16 valence electrons available for this compound. Next, I need to figure out what my central atom is going to be. So my central atom is going to be the one that can make the most bonds. Carbon has 4 valence electrons. It needs 4 more, so it's able to make up to 4 bonds. Oxygen has 6 valence electrons. It needs 2 more to achieve an octet, so it can make 2 bonds. So carbon is going to be my central atom. So I'm just going to place my 2 oxygens and connect them with a single bond. So in that single bond, there's 2 electrons. So because I've placed 2 bonds here, I now have 12 valence electrons remaining. So now what I need to do is just to take those 12 and just place them around the outer atoms. So I'm now out of electrons. Now I need to check to make sure that everybody has their octet. So looking at oxygen, remember that there are 2 electrons present in each of these bonds. So oxygen is going to have a full octet on both sides, but carbon only has 4. So I'm going to take some of these electrons that are lone pairs here, and I'm going to move those into the bond. And then I'm going to do the same thing on this side also. So this is still 16 total valence electrons, but by moving some of those lone pairs into the bond, now carbon has 4 total bonds, which means 8 valence electrons. So let's go ahead and take a look at carbon tetrachloride. So again, we have carbon with its 4 valence electrons, and then we have 4 chlorines. Each chloride is going to have 7 valence electrons. So if I multiply that by my 4 chlorine atoms, this is going to give us 28 valence electrons. So that means that I have a total of 28 plus 4, which is 32 valence electrons. So my central atom is going to be carbon. A lot of times carbon is the central atom because it can make 4 bonds. Chlorine needs 1 more valence electron to have an octet, so it can only make 1 bond. So I know that carbon is going to be my central atom here. So I have 4 chlorides that I need to attach to this carbon. So I'm going to start just by attaching those with single bonds here. So each of those single bonds is 2 electrons. So I've added 2, 4, 6, 8 electrons so far. So that's going to leave me with a total of 24 valence electrons. So now I'm going to take those and just distribute them around the outer atoms. So there's 12, 18, and now 24. So now that I've drawn this, I need to check to make sure that everybody has an octet. So each of these single bonds is 2 electrons. So carbon has its 4 bonds, which means it has an octet. It has 8 electrons. Each of these chlorines is going to have an octet from the 6 lone electrons plus the 2 that are in the bond, giving us 8 total. So now that we've predicted the Lewis diagram here, we want to try to figure out what this would look like in 3 dimensions. So that's what the VSEPR shape tells us. VSEPR is short for valence shell electron pair repulsion. In other words, all of these electrons, whether they are in bonds or they are lone pairs, repel each other. So this pushes the bonds and those lone pairs as far apart from each other as possible. So to figure out the VSEPR shape, we need to look at the Lewis diagram and we need to check 2 things. So first, we need to see how many atoms are bound to the central atom. So in the case of carbon dioxide, we've got 2 atoms on the central carbon. Then we have to check for lone pairs. So lone pairs are electrons that are not in a bond. We only care about the central atom. So the ones that are on oxygen, those aren't going to make a difference to us. On carbon, there are 0 lone pairs. So now we need to look at our VSEPR chart and identify what shape is going to correspond to those values. So 2 bonded pairs and 0 lone pairs, the shape is linear. Now looking at carbon tetrachloride. So my central atom is carbon, and this time we have 4 atoms attached to the central carbon. We again have 0 lone pairs on the carbon. So I'm going to go ahead and take a look at that VSEPR chart. So I'm looking for 4 bonded electron pairs and 0 lone pairs. So this corresponds to the tetrahedral shape. So how many electrons are shared in a single, double, and triple bond? Single bond is going to be 2 electrons. A double bond is going to be 4 electrons. And a triple bond is going to be 3 electrons. Or excuse me, not 3, 6 electrons. The next question asks us to predict which of the following is going to have a higher boiling point and to explain why. So what we're looking for are the intermolecular forces that are present in both of these molecules. So to start, dispersion forces. Dispersion forces occur in all molecules. So if it's made of nonmetals, if it's a molecule, it's going to have dispersion forces. These are really weak attractions between molecules due to temporary dipoles. Next strongest type is going to be what we call dipole-dipole. This is present in anything that is polar. And lastly, the strongest type of intermolecular force that we talk about here of these 3 is going to be hydrogen bonding. So this is where you have a hydrogen attached to an F, O, or N in a molecule. What happens is the H of one molecule attracts the F, O, or N on a different molecule. So simply having those bonds present can tell us if we have hydrogen bonding or not. So let's take a look at A. So we have methane and methanol here. So both of these are molecules. So these are both going to have dispersion. Dipole-dipole occurs in polar molecules. So a quick way to test for if something is polar or nonpolar is to check the symmetry. So if we look at these 2 molecules here, if I cut this guy in half, it doesn't matter how I do it, it looks the same on both sides. So this is highly symmetrical, which means that it's going to be nonpolar. If I cut methanol in half, the 2 halves are not the same. So it is asymmetrical, which means that we also have dipole-dipole. In order to have hydrogen bonding, we need a hydrogen attached to an F, O, or N. So I don't have that in methane. Those hydrogens are all attached to carbons. I do in methanol have a hydrogen attached to an oxygen here. So this one is going to have hydrogen bonding as well. So between these two, the one with the higher boiling point is going to be methanol. And that's because it has much stronger intermolecular forces. Boiling something just means that we are taking a liquid and we are converting this into a gas. So we do that by adding heat, which disrupts those intermolecular forces. So on something like methanol, because those forces are stronger, it's going to require more heat to disrupt those attractive forces. Next, we have H2O and H2S. So these are both molecules. They're made of nonmetals. So these are both going to have dispersion forces. These are also both polar. If you cut them in half, the two parts, the two halves, are not the same. So we have dipole-dipole interactions as well. In order to have hydrogen bonding, we need a hydrogen attached to an F, O, or N. So we see that in water, but we do not see that in H2S. So the one that's going to have the higher boiling point, again, is going to be the one that has stronger intermolecular forces. I'm going to need more heat to disrupt those stronger attractions, allowing this to change from a liquid to a gas. Now we want to go ahead and fill in this table by writing in the name or the formula. So the first one that I have here is Cu2SO3. So Cu is copper, which is a metal, and SO3 is a polyatomic ion. That's sulfite. So this is going to be an ionic compound. So if I want to write the name of an ionic compound, first I'm going to write my cation, which is going to be copper. Now, copper is a transition metal, which means that we don't know its charge. So I need to figure it out and write it as a Roman numeral. So I don't know the charge on Cu, but I do know that sulfite has a -2 charge. There's only one sulfite present here. So that means my positive charge has to be +2. There's 2 coppers. So each of them must be +1. So this is going to be copper 1 sulfite. My next compound, I have lead 4 chloride. Lead is a metal, chloride is a nonmetal. So again, we have an ionic compound here. Lead is Pb. And this Roman numeral is indicating me that the charge on the lead is +4. Chloride is Cl with a -1 charge. So that means that my formula has to be PbCl4 so that my charges are overall going to be neutral. Next we have Na3PO4. Sodium is a metal, and phosphate is a polyatomic ion. A good hint that you have a polyatomic ion is to count the number of elements that you have. I've got 3 elements here, so there's a good chance there's a polyatomic ion. So this is going to be an ionic compound. So first I need to name Na, which is going to be sodium. We always know that sodium is going to be +1 because of its position on the periodic table. So I don't need a Roman numeral here to indicate the charge. So now I just need to name PO4, which is phosphate. Next we have sodium sulfide, IDE. So whenever you see IDE, That's indicating to you that this is a monatomic ion, sulfide, which is a nonmetal, and sodium, which is a metal. So we have, once again, an ionic compound here. So sodium is Na, and it always forms a +1 charge. Sulfide used to be sulfur. It has a -2 charge. So that means that my formula has to be Na2S. Next we have NH3. So nitrogen and hydrogen are both nonmetals, so this is going to be a molecular compound. That means that I'm going to use my prefixes here. Now there is only one nitrogen, but one of the rules is that you never start with mono in a name, you just start with nitrogen. So this is going to be nitrogen, and there's 3 hydrogens, which is tri. Hydrogen will become hydride in a compound. Next we have hydrophosphoric acid. So we know that this is going to be an acid. So the fact that this is hydro-blank-ic acid tells me that this originally ended with "ide." So this was originally phosphide. That's just phosphorus with a -3 charge. Now, since this is an acid, we're going to need to put an H in front. Hydrogen always has a +1 charge. So in order to make this neutral, I need 3 hydrogens for each phosphorus. Next up, if we look at this one, we know again that we have an acid here. And I know that because it starts with hydrogen. So I need to figure out what this is called. So this is the polyatomic ion acetate. It ends with ATE. So whenever I name this acid, I'm going to name it as a blank-ic acid. So this is going to be acetic acid. That's the acid present in vinegar. Next up, we have another acid. This time it's an us acid. So that indicates to me that this chlor originally ended with ite, I-T-E. So originally this was chlorite, which is going to be ClO2 with a -1 charge. We need to put a hydrogen in front because this is an acid, and those charges are already balanced. So HClO2. Next, N2O5. So this is going to again be molecular because we have nonmetals. I've got 2 nitrogens, so that's going to be dinitrogen. And there are 5 oxygens, so that's penta. Oxygen becomes oxide in a compound. Next we have silver bromide. Now, a lot of times whenever you see silver compounds, you might see it as silver 1. Silver always has a charge of +1. So silver is a metal and bromine or bromide is a nonmetal, so that makes this an ionic compound. So silver is Ag and it is always +1. Bromide is Br -1. So my formula is just simply AgBr. Next up, we have PbSO4. So Pb is lead, and SO4 is a polyatomic ion. So this is an ionic compound. So we're going to start with lead, and we don't know the charge of lead, but we do know that the charge on sulfate is -2. So since there's only a single sulfate here, the charge on lead has to be +2. So this is going to be lead 2 sulfate. Next we have titanium 2 acetate. So titanium is a metal and acetate is a polyatomic ion, so we have another ionic compound here. Titanium is Ti, and the charge on this titanium is 2. acetate is C2H3O2. That is a single acetate, and that has a -1 charge. So that means that I'm going to need 2 acetates for each titanium. So I need to put a parenthesis around the acetate there so that I know that it's 2 acetates and not C2H3O22. This table is about different bonding types. So we have ionic, metallic, polar covalent, and nonpolar covalent bonds. So an ionic bond is the attraction between a cation and an anion. This occurs between a metal and a nonmetal, or there could be a polyatomic ion. So in order to get a cation and anion, one atom is going to give up electrons and the other will gain them. So electrons are transferred from one atom to another. And an example of that would be sodium chloride or table salt. Metallic bonds occur between electrons being shared in a C. So this only happens in metals. And those electrons are going to be shared amongst all of the metal atoms. And this is what we would see in any of our metallic elements like gold, Au. For polar and nonpolar covalent, both of them involve sharing electrons between only 2 atoms, but that sharing could be equal in the case of nonpolar or unequal in the case of polar. So this occurs between nonmetals. Now, in covalent compounds as well as in metals, electrons are shared. The difference is how they are shared. So in polar covalent and nonpolar covalent, those electrons are specifically held between 2 atoms. That is localized electrons. In metallic bond, those electrons are shared between all of the atoms, not just 2 that are next to each other. So this is going to give us the properties of metals, like them being shiny, good conductors of heat and energy, electricity, and malleable. You can hit them with a hammer. So in number 5, we have some more Vesper shapes to determine here. So let's start by looking at HCl here. So HCl is just 2 atoms sharing a single covalent bond. So we don't really have a central atom. So I can't really tell you the bonding or lone pairs on a central atom. As far as the shape here, this is really easy because it's just 2 atoms. The only way to connect 2 points is with a line. So this one's going to be linear. Next, we have carbon dioxide. We have 2 bonding atoms and 0 lone pairs. This is going to also correspond to a linear shape. Next, we have NH3. So we have 3 bonding atoms and 1 lone pair on the nitrogen. So looking for 3 and 1, this is going to be trigonal pyramidal. So knowing the shape is really important for understanding the polarity of a molecule. So let's think about water here. Whenever you draw the Lewis diagram for water, you might draw it like this. This would be a correct Lewis diagram. But this gives you the false impression that this is going to be linear and thus nonpolar. When you consider the fact that there are 2 bonding atoms and 2 lone pairs, this is actually going to have what's known as a bent shape. So that's going to be something more like this. So because of that bent shape, water is polar as opposed to being nonpolar. So we want to determine how polar bonds are going to be between 2 different atoms here. So I just want to get the difference in electronegativity. So I'm just going to do the value for hydrogen, which is 2.1, minus the value for chlorine. And those straight lines are just indicating that this is an absolute value. I only care about the difference here. I don't care about whether it's positive or negative. So a difference of 0.9 is going to indicate to us that we have a covalent, moderately polar bond. Next we have H and O. So we have a little bit of a bigger difference here. So this is going to correspond into very polar covalent. And then looking at carbon and hydrogen. So again, I don't care about whether it's positive or negative. I just care about the difference here. So that is kind of right on the edge in between moderately polar and nonpolar. So we would say that this is very slightly polar or moderately polar. But we also might consider this to be nonpolar. So this bond has some polarity, but not very much. So we want to use symmetry to determine if these are polar or nonpolar. So I was discussing about how water has this bent shape. So if we cut this in half, it's not the same on both sides. So that's asymmetrical, which means polar. For Cl2, no matter how I cut this, it's going to be the same on both sides. So this is going to be nonpolar. The last one here, if we think about symmetry, we might think that this is polar, but we have to look a little bit more closely. We have a plus and a minus. I have a cation and an anion. So this is actually an ionic compound, which means that it is neither polar nor nonpolar. So for question 8, which of the following will dissolve in cyclohexane, a nonpolar substance? So what we want to think about is like dissolves like. So if we have a nonpolar substance, that's only going to dissolve in a nonpolar solvent. So we can eliminate NaF right away because this is ionic. That's not going to work. CO and HCl are both going to be polar. And I know that because those are just two atoms and they're different atoms, so they're going to have different electronegativity values. I2 is going to have two identical atoms, which means no electronegativity difference. So the one that will dissolve hexane is going to be I2. Here, we want to look at these ionic formulas and determine which ones are correct using their charges. So for A, I count 3 different atoms here. So I have a polyatomic ion. So potassium has a +1 charge, and MnO4 is the polyatomic ion permanganate, which has a -1 charge. So A is a correct formula because I need one of each to make neutral. K, again, is +1. OH is the polyatomic ion hydroxide. Once again, we need a 1-to-1 ratio because we have a +1 and -1 charge. So KOH is a correct formula. Looking at calcium phosphate. Calcium forms a +2 charge, and phosphate, PO4, forms a -3 charge. So in order for this to be neutral, I'm going to need 3 calciums to make +6, and I'm going to need 2 phosphates to make -6. So C is not correct. The formula should be Ca3 parentheses PO4 2. Next up we have NaCl. Na has a +1 charge, Cl, chloride, has a -1 charge. So my formula should be just NaCl, not NaCl2. Here we have molecules. Some of these are going to be named incorrectly. So we want to figure out which ones they are and then name them using, correct their name. So here I have CaH2, and we're calling this calcium hydroxide. So this name does not match this formula. If I want calcium hydroxide, calcium is Ca with a +2 charge, and hydroxide is OH with a -1 charge. So my formula should be CaOH2. So because I have calcium hydroxide, a metal, and a polyatomic ion, I know this is covalent, so I need my charges to balance out to neutral. Next we have H2CO3, and we're calling this carbonic acid. So carbonic acid, this is an ic acid, this originally ended with 8. So originally we had carbonate. Carbonate is CO3 with a -2 charge. Since this is an acid, I need to put a hydrogen in front, and that charge is +1. So I need 2 of them. So this formula is correct. Looking at C, we have iron sulfate, FeSO4. So the problem with this one is that iron is a transition metal, which means we don't know its charge. So for iron sulfate, I need to figure out what Roman numeral I need. Sulfate has a -2 charge. There's only one sulfate here, so the iron is going to need to be +2. So this should be called iron 2 sulfate. The last one here we have calcium hydroxide. So we already saw that that formula is the real formula for calcium hydroxide. Next we have H2SO3, which we're calling sulfuric acid. So if I have an ic acid, that means this originally ended with 8. Sulfate is SO4 with a -2 charge. So this isn't going to be correct because we have sulfite here. So sulfuric acid should be H2SO4. H2SO3 is not sulfate, it's sulfite. So H2SO3 is actually going to be sulfurous acid. Next we have chromium 2 nitrate. So nitrate, NO3, has a -1 charge, and there's 2 of them. So the total negative charge is -2. So the charge on chromium should be +2. And this all matches here. So this formula is correct. Next we have potassium cyanide. So the problem here is that we actually don't need a Roman numeral. So potassium always has a +1 charge. So I don't need this Roman numeral here, and this should just be potassium cyanide. Next we have nitrogen trioxide. So nitrogen with no prefix here means just 1, and trioxide is 3. So this is different from nitrate. This is a molecule of NO3, whereas nitrate is an ion of NO3. So nitrogen trioxide would be NO3. So if I want to do N2O3, that's going to need to be dinitrogen because there's 2, and trioxide for the 3 oxygens. So, number 11 says to use the electron C model to explain why metals are good conductors and are good conductors of electricity as well as being malleable. So, in the structure of a metal, we have these metal cations that are surrounded by an electron C of these delocalized electron. So this means that metals are going to be malleable. If you hit the metal, these cations can just slide past each other without repelling. So this means that when you hit a metal with a hammer, it bends rather than breaks. And electricity is just a flow of electrons. And in metals, we already have flowing electrons. So they're going to be good conductors of energy. Number 12, we want to explain some periodic trends. And we're talking about shielding. So shielding refers to how many layers of electrons are present in a molecule, or in an atom, rather. So electronegativity is a measure of how attractive an atom is to electrons that are being shared in a bond. So as we get more layers of electrons going down a group, column, or family, so this is group, column, and family all mean the same thing. We're talking about up and down, a column. So as we get more layers of electrons, the attraction between the nucleus and the outer electron gets weaker. So my electronegativity gets lower. It's less attractive to electrons. Ionization energy is how much energy I need to remove a valence electron. So as we get more layers of electrons, the attraction between the nucleus and the outer electrons gets weaker. It's easier to remove an electron, so we require less ionization energy. As we go down a column, the atomic radius also increases. This is because we have more layers of electrons. The attraction also gets weaker, so those electrons aren't going to be held as close to the nucleus. So that means that our atomic radius is going to get larger. Next, we want to look at nuclear charge. So this is the charge on the nucleus. So how positive the nucleus is. So as we go across a period, a row, or a series, those all mean the same thing. So we're talking about left to right. So as we go across a row, we're gaining more protons in the nucleus. We do also gain more electrons, but those electrons are being added within the same energy level. So they're not going to be any farther away from the nucleus. So as we go across the row, the nucleus becomes more positive. There's a stronger attraction, which means higher electronegativity. As we gain more protons and that attraction gets stronger, it's also going to be more difficult to remove an electron. So that's going to be higher ionization energy. And atomic radius is going to decrease because as that attraction gets stronger, those electrons move in closer and we end up with a smaller radius.